Swayam Prabha. Digital India. Educated India.
Welcome to this lecture in soil technology. My name is B.S. Das. I am from Agricultural and Food Engineering Department at the Indian Institute of Technology, Kharagpur. Today we are going to discuss about soil water energy status. So we will look at three important concepts. The first one is soil water potential. Then we will talk about water retention characteristics and how to measure soil water potentials. So some of the key concepts we are going to discuss about field water balance and forces acting on water. Then we will talk about key concepts of fluids from our basic understanding of surface tension, contact angle, then the capillary pressure, and the rise of water into the capillary tubes. We will then look at soil, as a bundle of capillaries, drawing an analogy between a perfect capillary tube and the zigzag soil pore network. Then, of course, we are going to look at the potential energies involved in water retention. We will then, of course, look at the potential gradients as the driving force for water to move through soil, introducing into soil water flow. So, first one, the field water balance. As all of us now know, that the soil retains water. So, essentially, when we add water from different sources, whether it is precipitation, meaning the addition of water from the atmosphere through either rainfall, snow, fog, or any other kind of water addition from through the atmosphere into the soil. Then, of course, we have the irrigation water. We also sometimes have water flowing into the soil laterally. And so these are the different kinds of the ways that water is added to the soil. And of course, soil does not retain all this water which is added. Some of the water gets lost through either evaporation or transpiration. We have sometimes difficulty in separating out the evaporation and the transpiration component. So we generally tend to lump these two parameters, the evaporation and transpiration, into evapotranspiration. Water is also does not stay in soil. It could really percolate down through the process of drainage or deep percolation, and then, of course, not all the water stays on the or infiltrates into the soil. Anytime the addition of water that exceeds the capacity of the soil to infiltrate, the excess water is going to be run off in form of the overland flow. Water may also leave from a control volume of soil through lateral flow in form of seepage. And so you have bunch of different ways that water is added to soil, and bunch of different ways the water is lost from the soil. So if you're looking at a if you're looking at a soil profile, for instance, let's say if you have a deeper soil profile, and if you have you're looking at water as a function of soil depth. Imagine that you have a wet soil today. So these are essentially, maybe you measure the water content at different locations and sort of created a soil water profile today at some time t. And then, of course, if you are to come back tomorrow and look at the soil profile, and if for any region there is a change in the soil wetness, you are going to see a different soil water content profile. Of course, the loss of water from this profile, is going to be actually this difference in the soil water depths that you can really calculate using our concepts of equivalent water depth. And so this difference in the storage, we designate is, it's a delta S, is therefore all the water which is there in the soil profile today, and maybe after a say 24 hours time or any other time interval, if the soil wetness decrease, and so whatever that decrease that you really come across, that becomes your storage change. And you could either write in terms of the equivalent depths, add them together, layer wise, or you can also think about water content as a continuous function of the soil depth. So if you do that, then of course you could replace these summation signs in terms of these integral signs. Essentially, both of them really are the same. One treats the soil as soil water content as kind of discrete function of the soil depth, whereas the other one looks at more like a continuous function. And in both the cases, what you see is that there is kind of a change in the soil water storage, right? And so this essentially means that all the water which is added to the soil does not necessarily get drained out of the soil profile. Some of the water is pretty much left out in the soil profile. You know so this allows us to think that there must be some ways that soil is able to hold water. That means that there must be some kind of an attractive force between the water and the soil, so that soil is able to really hold the water, and the gravity almost fails to drain that water instantaneously, as you would really assume if you are putting water in a pipe, and at the moment you really take out the pipe, of course the water is going to get drained out very quickly, whereas in case of soils, something really holds the water. And so therefore, when you look at these specific forces that might be responsible for holding the water inside the soil, you could broadly think about two different groups of forces: the small scale ones and the short range ones and the long range ones. This for the short range ones, the two forces of van der Waals force and electrostatic dipole effects basically arise because the soil, as you remember, one of the component of the solid phase is the clays and soil organic matter. Both tend to hold some unbalanced negative charge, and so excess negative charge, and so therefore they have the capacity to attract the positive head of the pole of the water molecule. As you know, water is a dipolar compound, and so dipolar molecule, and so you will find that the positive and the negative poles of the water would be orienting in a fashion that is giving rise to van der Waals force between them. You also would imagine an electrostatic dipole, and that's because of the periodic structure of the soil clays. As you remember, clays are layered structures. You have one layer of alumina octahedra, one layer of silica tetrahedra forms a 1:1 lattice, and so you have number of such say for example, kaolinite having a 1:1 or a mortonite having a 2:1 structure, you will see that the stacks of kaolinite would have this characteristic periodicity in terms of the alumina octahedra and silica tetrahedra, and again alumina octahedra. So that's sort of a kind of a periodic structure that also give rise to some kind of a electrostatic dipole effect, for the polar water to be attracted to the clay surfaces. Both of these short-ranged forces basically occur when, perhaps a monolayer of water, sort of coming close proximity of the soil clays. So therefore, the distance between the water and the soil particles are very, very small. So you can pretty much assume that these water are almost like a bound water form, one or few layers of water molecules, is indeed very, very small amount of water, typically are not very relevant for our from the perspective of plants utilizing it. The long range ones, forces, are basically the interaction between water and solute. That is your osmotic uh, component of the force acting on the water, and of course the interaction between the soil solids and water. So you have water and solute giving rise to osmotic interaction, and water and soil particles give rise to the surface tension. And as you know, surface tension is basically a sort of a resultant of adhesive and cohesive forces acting between water and soil, and water and air, interfaces. So, as I mentioned, the attractive forces between the attractive forces because of the van der Waals force or electrostatic dipole effects are stronger. They are in the range of between water and the solid particles. The range of influence is very small, in the order of angstroms, whereas when you go to osmotic and the surface tension, you have you have water present almost in the range of influence of water is almost a millimeter away from the solid surface, and these are relatively weaker forces, so much so that when water is held in these kind of forces, plants would be able to extract at least portion of water from that soil water interfaces. So, coming back to the practical aspects of these forces, generally we disregard these van der Waals and electrostatic dipole effects on water. Most of the water that we are interested in are basically weakly held with the soil solids in form of this surface tension or interfacial energies and the osmotic component. So coming back to the the simple four simple principles that we really need to know to understand the interaction between the water water and soil solids. The first one is of course this cohesion and the cohesive and the adhesive forces. As you know, water is a very interesting molecule. You will in case of water, you will typically see that the water molecules inside the water are kind of balanced by the cohesive forces, but molecules that are present at the surface of the water, part of their force, intermolecular forces are unbalanced, which really puts some kind of tension on the the molecules that are present at the water surface, and so this concepts of surface tension comes in. We describe surface tension as the energy required to increase or stretch and the surface, in terms of a kind of a tension per unit surface area. So it's a ratio between the surface energy by surface area, and the interfacial tension is often called as the surface tension when the vapor phase or the phase of the non-wetting fluid is it the vapor of the wetting fluid itself. So in case is the air above the water is when it is saturated with the vapors of water itself. The interface between the vapor phase and the water is called the surface tension, and as you know, the surface tension is therefore expressed in terms of energy per unit area, which is almost equivalent to the force per unit length. And so for pure water, we know that surface tension is in the order of about 73 dynes per centimeter. And that of ethanol is, of course, a lot less compared to the surface tension of mercury. It's in the order of about 430 dynes per centimeter, almost almost more than 5 times or 6 times than that of the water. So this is one of the concepts that you already know, that surface tension is a property that describes the interfaces. Okay. One of the other concept that really we also need to understand is this wettability of the fluids. Essentially, what happens is these surfacial energies or the surface interfacial energies or interfacial tensions are characteristic of the interfaces. So when you are looking at water, in a contained in a solid container, you typically will have three different kinds of interfaces, and so the interface between the soil, between the water and the air, so basically liquid and gas, interface between the solid and gas, the container of the liquid, and of course the interface between the solid and the liquid. And as we have described earlier, at the interfaces there are unbalanced forces on the molecules. So therefore the adhesions, the attraction between the dissimilar atoms, and the cohesions would sort of give rise to interfacial energies or interfacial tension for all these three interfaces: solid, liquid gas, and gas solid. And as you can see in this narrative here, you can see that these three forces, because of the interface between solid gas, solid liquid, and liquid gas, sort of makes that water surface curve, and the angle measured from the solid to the through the liquid to the gas interface, liquid gas interface, is called the surface tension, called the contact angle. And so from the resolution of these three forces at the interface, one could pretty much derive at equilibrium a relationship among these interfacial energies, and so that allows us to write the cosine of the contact angle in terms of these three interfacial tensions. Gas solid minus the solid liquid divided by liquid gas is the magnitude of the contact angle theta. And so we typically say that a liquid is a wetting liquid when this angle is less than 90 degree, and a non-wetting, for a non-wetting liquid, it is more than 90 degree. So this relationship between the contact angle and the interfacial energies per unit area is basically the Young's equation at equilibrium. When you have a meniscus formed. And so this is again the second principle that comes from the fluid. The third one, of course, again is related. We know that this curvature that develops at the gas liquid interface, is a result of the resultant kind of force because of the molecules pretty much interacting, at the interface, typically creating a pressure difference across the interface. And generally, you will notice that the pressure because of the air is greater than air on the air side of the interface. Is gaseous side of the interface is more than the pressure on the liquid side of the interface. That's the reason why that surface is curved. So it's kind of concave upward, and so the again Laplace for this kind of an interface has showed that this difference in the pressure across this interface, this PA minus PW, which is called as the capillary pressure, is directly proportional to the surface tension and inversely proportional to the radius of the curvature. And so again, we have a relationship between this PC and surface tension and radius of the water containing the pipe. And the last one in this simple relationship that we will use is the capillary rise equation. As you know, once we really bring a capillary tube into the water, water tends to really move upward into the capillary tube because of the the excess adhesive pull of the water, and as upward force keeps pulling the water up, the downward gravitational force would really, have the water pull down, and of course at equilibrium you will see that these two forces ought to be equal, and so therefore again this surface tension force acting on the 2 pi r on the perimeter of the water meniscus, so if you multiply that with the surface tension, you have this total force because of the capillarity, and again here you have this the weight of the water because of this gravitational downward pull, and you can rearrange this equation, this equation, and you will be in a position to derive this relationship between the amount of between the height of the water above this free water surface. Here is the free water surface. From above this free water surface, whatever to the meniscus of the water inside the capillary tube is related to the surface tension and radius of curvature. Please note that this part of this capillary rise equation is also this difference between the pressure across an interface PA minus PW, and so this is your capillary pressure. So therefore, you could easily see that this HC is equal to minus PC over rho WGR. Rho is the density of water. Okay, so these 4 principles that we have studied in our basic fluid classes, we would be in a position to also apply in soil water system, the pore sequences that we have in soil, provided we make a lot of assumptions, because as you can see, these principles are with regular geometries, whereas when you look at our soil is not, the pore spaces in the soil are not straight capillary tubes, or you don't really get the shape of the pores and the size of the pores. They are all kind of random. This photographs that we, this cross section of the X-ray CT scan that we showed earlier, you can see that these pores definitely are not really a capillary, like a straight capillary tube. Of course, you probably can make some kind of an approximation. So here is a small cartoon that really explains that if you have an irregularly shaped pore channel, having the size, of course, not a very regular cylindrical like a capillary tube, as in this case. Nevertheless, you may be in a position to make an approximation for these pores, even is it looks kind of irregular in shape. You probably can sort of assume that these irregularly shaped pore can be approximated to be a sort of a straight capillary tube. Well, that's not enough. If you really look at any pore, continuous pore sequence, say for example, if I were to really think about this pores up here, you can see that these pores sort of goes like a zigzag, so it's not quite a straight line. And so if you are thinking about the distance, the length of this pore, just that Euclidean distance between these 2 points does not tell us the length of the pore. So therefore, again, you also have to introduce some kind of a scaling factor for that pore to be, kind of straightened out, so that the zigzag kind of nature goes away. Well, that's not the only assumption, So you have an irregularly shaped pore. You really convert to a regular shape. You have a kind of a bent pore. You kind of straighten it using some kind of a multiplication factor, but that's not enough. It's really, when it comes to soil, you have a bunch of these kind of pores. So again, you really, last approximation you do, well, you say that, well, soil sort of consist of maybe a bundle of capillaries, and maybe of regular shape. Only difference is they may be having different radius, different radii, and so maybe their radii of the pores may be statistically distributed, but still you will be in a position to really kind of think about, okay, I have this soil, I can visualize this of having straight capillary tubes passing through one end of the soil to the other end, and a bunch of them, and so I can think about soil to be almost like, as its pore space is pretty much can be reconstructed in form of a bundle of capillary tubes, if you imagine, right? Now, if you do that, of course, in a soil, when you look at of different pore sizes, and if you want to really apply this capillary rise equation and sort of link the radius of the pore to the height of water that you are going to see, we know that soil pore sizes, we have described this when we talked about the soil structure. You have micropores and the majopores, and the largest size pores are macropores, and of course each of their sizes, if you really convert it, so this radii, if you take the radii of these and put it that in that relationship between capillary rise equation, you see that this the height of water into the capillary, provided if it's just a single capillary, would go to more than almost 300 centimeters when your pores or micropores. We're talking about 3 meter to a height of 3 meter. The water can rise above the free water surface if the pore sizes are less than 10 micron in size. Of course, that's one of the reason why very fine textured soils with lots of clays have larger water holding, water retaining capability than a macroporous soils where the pore sizes are very large, and so typically water is not going to be easily retained by macropores. They easily get drained because of the gravitational pull. Okay, one of these, so once we know these sort of relationships, the next thing that really comes to us is to really think about how water would, of course, move in such porous medium. So if you think about water, some mass of water moves from one location to the other. Let's say you have a location S1, and it really moves to the next location, which is S2, because some a bunch of forces, with a net force, with a finite net force acting on it. Of course, in doing so, one of the thing that would happen is that the potential energy of the water when it was at S1 would really decrease to a smaller or lower potential energy when it reaches S2, because part of that energy is basically utilized in doing that work of moving from location S1 to location S2. And so for a second, if you really define a water potential to be the ratio between the potential energy to mass, okay, you would be in a position to write an expression for this potential energy in S2 and the potential energy minus at S1. And so you will have this delta psi, where psi is defined as the potential energy per unit mass. This delta psi, of course, is going to be less than zero, right? Because this is smaller than the potential energy at S1. And so if you are to therefore write this potential energy now in terms of the work done because of a dot product of the net force and the displacement vector, okay, and divide that by m, of course, these, both of these are positive quantities, right? All of these are positive quantities. You have to really introduce a negative sign, so as to really take into account that water is moving from a higher potential to a lower potential, right? And so once you do that, of course, you can think about this delta psi to be very, very small, and so you could replace these deltas into differential form, so that you have some kind of an expression for potential in terms of the forces acting on it. So let's look at it a little bit in a more sort of a more schematic manner. So what we just said that if you have at S1, you have the potential energy PE1, and you have a potential energy PE2 at S2, and you define potential energy as potential energy per unit mass, and so you could say that this psi up here is more than psi1, because part of this energy is spent in moving from S1 to S2, right? And so therefore you are in a position to write these expressions. So what all I really discussed in the previous slide is basically schematically shown here in a cleaner board up here, right? You could, of course, define this potential in different ways. Instead of defining potential as a potential energy per unit mass, you can stick a gravitational constant, so that you now have a potential energy per unit weight. And as you know, the potential energy is equal to mg h, and so basically mgh divided by mg is your h, right? So that's kind of a head. So essentially the rise of water that we saw in a capillary tube is indeed, it's a potential energy per unit weight. And so similar to potential, we could therefore think about a potential head, and again do the same thing. We have a potential head S2, a potential head S1, and you could think about this potential energy in terms of this work done, the dot product of the two vectors, the force and the displacement vector delta S, and of course you divide that at mg. And of course, you need to really think about this the kind of forces that is acting on the water. As we discussed earlier, you could have at least four different kinds of forces when it comes to contact between water and soil or water and solute. And we said that at least the osmotic and the osmotic and the this capillary forces would be involved. So think about, and we know that water is also being attracted downward because of pulled downward because of the gravity. So the gravity would be another such force. So so eventually this water molecule would come from S1 to S2 because of the net forces, not because of any specific force. So therefore you could write sort of this net force as sum of these forces F1, F2, F3, and so on. And so for each one of them, you will have a component potential, and so that when you sum all of them, you will have a total potential head HT, right? So just like we could express potential energies per unit mass or potential energies per unit weight, you could also stick in potential energies per unit volume, and you can easily see that the potential energy per unit volume is indeed a sort of a term which has the same dimension as the pressure, a Pascal here, for example. So when we talk about energy per unit mass, we have a joules per kg. We have a potential energy in terms of per unit volume. You have a Pascal, and if you are talking about a potential energy per unit weight, you have a length dimension. So it's a meter. So you can therefore describe these potential energies in three different ways: either potential energy with per unit mass, or unit volume, or unit weight. So three different ways that you can express the same potential energy, right? So if we are to really look at the linkage between these potentials and the these new ways of describing these potential energies with all the basic principles that we really discussed about regarding fluids, so let us look at that combination. We know that the Laplace equation describes us the relationship between the capillary pressure, surface tension, and the radius of curvature. Similarly, capillary rise, as I mentioned earlier, can also be linked to the capillary pressure. So this up here is the potential energy per unit volume, a capillary pressure, right? This up here, a potential energy per unit weight. Of course, you could now you could now probably combine them. Here is a potential energy per unit weight, so it's a potential head. Here is the pressure potential, and of course we could also have some kind of a divide all through with the density, and you could see a ratio between PC over density of water should be equal to the potential, which is potential energy per unit mass. So you could really, therefore, these three forms of the potentials we just described, you would be in a position to interrelate them through these basic principles of fluids that we just studied, right? So typically for the soil water potential, we recognize four distinct components, four distinct forces that that act on water. So you can kind of think about the first one up here is the gravitational potential head. Here is this one is the potential head because of this capillarity, because of the interaction between water and soil, right? This is because of the gravitational pull, and then also this is about osmotic potential head, and a fourth component we are introducing here, it's called the pneumatic potential. Many times also you will see that in soil there will be trapped air, which would be compressed because of the weight of the water and soil. They really would also have some force acting on the water. So these four components of the soil water potential head. So we talk about the gravitational potential head because of the gravitational field. And these three are basically because of the contact. This is because of the contact between the water and water and soil. When the contact is between water and water, we call it a pressure potential. When a contact is between the water and the soil, we call it a metric potential head. And this is the interaction between the water and solute. So that is an osmotic potential. Here is an interaction between water and air. So air basically is exerting a pressure on the water. So that's a pneumatic potential head. So these four components primarily, coming out of the four different origins. Here is because of the air, because of the solute, because of the gravity, and because of the water and soil, right? Water and water is only pressure. It's a hydrostatic head, and water and soil is a metric. And we'll see that a little bit more. So these potentials that you really come across, also need to be, for us to be able to use them, we also need to really kind of understand one of the concept of the reference soil water potential. So let's look at one of these. I have really included one of these components, the gravitational one. It's easy to really visualize. So our definition of the gravitational potential is the dot product of the gravitational force times the displacement vector. The dot product up here, meaning that this is equal to the force of gravity and the displacement times the cosine of the angle between these two forces. Okay, and so think about, if you are kind of setting up a sort of a coordinate system where the z coordinate axis is directed upward, and if you have water moving basically downward because of the gravity, so the force due to gravity acting downward, and the displacement vector goes upward, and so for you to really resolve it, you need that angle between these two forces. So basically you sort of replace this delta S with delta Z cosine alpha. This alpha is the angle between this gravity, this Fg up here, the gravitational force, and here is your displacement vector ds. Okay, and so because this angle is 180 degree, cosine of 180 degree is -1, and so therefore this -1 and -1 becomes +1. This mg and mg cancels out, so you have this expression, dhg is equal to dz. Now, if you integrate this expression both sides, you will see that an expression of this sort comes up, right? You have hg at z2 minus hg at z1 should be equal to z2 and z1, right? So because if you integrate that on both sides, right, that's what you get. So one of the things necessary for us to know, suppose you would like to really find out what is the gravitational potential head at point Z2, okay, we know where the Z2 is, but we need to know these two, this value of Hg at another known condition. So as a sort of convention, what we do is we assume that wherever this Z1 is 0, this gravitational potential head is 0. So implicitly we sort of have an arbitrary reference we are setting up. We assume that the gravitational potential head or the reference potential head for the gravity is 0 wherever we really choose z equal to 0. So that's kind of the convention. So once you do that, then of course these goes to 0, these goes to 0, and so therefore you are left with an expression for hg at any z2, right? And so we could replace essentially hg at any z, right, is equal to z. So, but this requires that the coordinate system, the z-axis, must be defined in such a way that it directs in the upward direction, not towards the direct. It should always be positive upward. With that convention, you really set this expression for the gravitational potential head. So this is your reference potential. So when you deal with these potentials, you always need to have a reference potential, because potentials are scalar quantities. You need to always look at the differences in potentials, because remember this from the definition itself, this here is it's a differential, it's a difference in the potential head, and so you need to really think about difference from where, and so that reference is important. So for the gravitational one, the reference is easy, because you just say that, well, wherever I start my z equal to 0, there itself I'll say that my gravitational potential head is 0, and above it is positive, below it is negative. That's what is the reference is doing. But similar to the reference potential for gravity, we also need to have reference potential for the other three components, specifically the metric or pressure potential head, and osmotic, and the pneumatic potential head. So for the metric or pressure potential head, the zero potential head. So basically, we are setting a zero potential head. For all reference, basically means you are setting a zero potential head. So zero potential heads is set for the pre-water surface for the metric or pressure potential, and zero potential head for the osmotic is defined when water contains no solute. There is no osmotic potential develops when, remember, the osmotic potential has to be proportional to the concentration of the electrolyte present in a solution. So when there is no electrolyte, so that is the zero potential. Similarly, for pneumatic, when the air within water is neither compressed nor compressed nor expanded, so it's atmospheric pressure. So that is again a reference potential for the pneumatic one. for most practical purposes, unless you have a salt affected soil, or you have sort of a standing water under pressure somehow, you basically deal with only two potential components of the potential. Either it's a gravitational potential always, and or you will have you will have both. You will have either a metric potential when the soil is unsaturated, when a pressure potential when soil is saturated with the presence of a over lying water layer. So basically, when you have a ponded water condition, you have excess water condition, you will have a positive pressure or a pressure potential head. Otherwise, it's a negative metric potential head when soil is not saturated. All of these concepts that we are developing, all this really applies, to a single capillary tube. But as we have really mentioned that, soil is not a single capillary tube, rather it's a bundle of capillary tubes. So what you could really do is that, well, so be it. Let this bundle of capillaries now drift into the water. So what would happen? This, depending on the size of this capillary tube, water is going to rise into the capillary tube differentially, right? So there will be, depending on the radius of the pores, you should be able to say, well, to what height water would rise into this capillary tube, sort of of course, at equilibrium, right? Because this happens when this upward capillary pool and downward gravitational pull holds the water inside the capillary tube at equilibrium. So there is kind of a hydrostatic equilibrium condition, right? And so how would you do that? Well, you put this capillary tube, bundle of capillary tubes in water, and assume that water rises into it. So at equilibrium, you will notice that some water enters into it, and suppose if you were to really calculate how much water is there at a cross section, you should be able to find out what is the volume of water from in each capillary tube, wherever the water is present, and depending on how much water is there, and suppose you want to really now kind of find out, okay, each of these R should have this should be like a R1, R2, and R3. So you should be able to think about replacing this R1 with an H1, right? And so and then of course, if you really divide this V with VT, right? So all that divided by VT, right? So what you should see is that, well, this is our what? This is actually water content, volumetric water content theta, right? This theta, we have defined it as volume of water per unit volume of unit total volume of soil. So what you see is that this amount of water present in this in a bundle of capillaries, the so-called the soil approximation for the soil, is uniquely linked to the radius, of the pore at a specific level of equilibrium, right? And all that is also uniquely related to this metric potential head, right, of water, because this H is the rise of the water inside the capillary tube. It's basically interaction between the water and in a capillary tube. This because of the adhesive forces, right? So that's the interaction term between water and the capillary tube. So capillary tube is basically representing our soil now. So soil solid, right? So it is the interaction between the solid soil solid and water. So what you see is kind of a at equilibrium, right? The water content present in a bundle of capillaries is linked to some kind of an equivalent radius, which is linked to an equivalent height of water through the capillary rise equation up here, right? That's our capillary rise equation. And so the moment you really disturb that equilibrium, you will see somehow another equilibrium is established, right? So at every hydrostatic equilibrium in soil, you will see that the amount of water which should be present would be uniquely linked to this HC. But what is HC? H is a measure of the potential energy per unit weight of the water. So here is this linkage. Here is this unique linkage between the water content, the volume of water, and the energy with which it really is held by the soil particles, right? And of course, these are essentially a hydrostatic equilibrium condition at kth kth equilibration condition. You have a relationship between unique relationship between theta and some kind of an equivalent radius and some kind of a corresponding equivalent the h or the potential head. So this is what you will see the moment really this equilibrium condition change. You can see that retention, the relationship between the water content and this energy content, this is you get a unique point. And so each of these points are unique equilibrium conditions, and if you kind of connect them, you get a complete sort of characteristics of how how much water is held, say how much water is held, at how much energy that holds it, right? So that's basically a linkage between the energy content and the content of water in soil is called a water retention characteristics. Okay, and this unique relationship between water content and soil water potential head is called a water retention characteristics. And remember, when we talked about these field capacities or wilting point, so those related to one of the points in this water retention curve. So if you are thinking about a field capacity to be about 0.3 bar, which is about 33 kilopascal. So here is minus 33 kilopascal, and so here is that field capacity of water. Similarly, as you really go beyond that to about 1500 kilopascal, so that's about 15 bar. 100 kilopascal is 1 bar, so that's about minus 15 bar. You will see that somewhere up here, somewhere corresponding to that, you will have a kind of a permanent wilting point. So these field capacities and permanent wilting points are kind of hydrostatic single points, equilibrium points in the water retention curves, right? So this is the relationship between the energy content and the water content. And of course, you could have a model such as this, where you can link the relative saturation with this metric potential head. Here, this alpha and m are basically soil specific constants. Okay, so we sort of we sort of understood about how these hydrostatic equilibriums work, and they give rise to this unique relationship between water retention characteristics, between the water retention behavior and the energy content of the soil water potentials. Here is a so how do we really measure the soil water potential? And again, here is a unique opportunity. This this equipment is called a tensiometer. This is basically it's just a hollow pipe up here, which is have an opening. You could just fill up this pipe with water and cap it, closely seal it. At the bottom, you have a porous ceramic cup. And this porous ceramic cup is unique in that the pore sizes are almost equal to each other, and it allows water to really enter into the this tensiometer, and so basically it can allow this water to go in or come out, but it won't allow air to go in. Okay, so the moment if you put this thing in soil, think about you are putting in this soil. So water, if water is dry, of course water will start coming out in all direction. It would come out, and as water comes out, the top is sealed, and so therefore what would happen, it would create a vacuum inside this, right? And because air cannot pass in to really neutralize that vacuum. And so that vacuum, you can measure it, maybe put a vacuum gauge, or you could put a manometer, or you could really put some kind of a pressure transducer, so that electronically you can measure it. And so this device helps us to measure the metric potential, or that interaction between water and soil in the soil at an equilibrium condition. And this is how it is done. Remember, we have described this total potential as a function of this dot product of the net force times the displacement, right? You can imagine a scenario up here when soil sort of comes in equilibrium with this, the water comes in equilibrium. So you know what, no more change, no more entry or exit of water from the tensiometer or into the tensiometer. An equilibrium condition is reached, for example. What would happen, that at that condition, water flow across that ceramic cup would stop, right? There is no flow. That means the net force acting on the water is going to be zero, and so this whole right hand side of this should be equal to zero. So therefore dHT equal to zero. Therefore, if you integrate that, this you will get dHT as a function of this coordinate s, the distance or displacement coordinate is going to be a constant, right? So this means if you really select 2 points at equal height, okay, so up one point here, another point up here, so that the gravitational head gradients are equal, because they are at the same height. No matter where you really draw a reference potential, the height of this point and the height of this point are same, right? So if you are to write down the hydrostatic total potential head to be constant, that means both inside the cup and outside the cup has to be equal, then of course this graph, the first one that you can really cancel out is the gravitational potential head, right? Because they are equal in the magnitude, and both they are equal in the magnitude. You can also think about this soil to have very little soluble salt, so this osmotic component part you can just cancel out. You can also think about soil outside the cup. It's an open system, no compressed air, no expanded air, so you could think about these to go to zero, right? This to be equal to, you can set it to zero. Well, in the right hand side, you have left out only this metric potential head. In the left hand side, you both have a metric potential head component and this pneumatic one, which measures this vacuum developed because of this water coming out of this the cup, right? Now let us think about this metric potential head for a second. This is what, this is the interaction of water present in the, present in these pores of the ceramic cup. It's a thin ceramic cup, and so water present there, would really, of course, would really enter into those, as a little bit of capillary effect is going to be there. But what is the thickness of the ceramic cup? It's a very thin one. So you could practically set these to be negligible. So therefore, the vacuum created inside the tensiometer is equal to the metric potential head, which is developed in a particular soil. So this measurement device is called the tensiometer, and is very frequently used in measuring the soil water potential, head in field conditions. So, okay, to summarize, therefore, what we have done in this class is we discussed about this field water balance and how water is retained because of the different forces, at least the long range ones, the capillarity and the osmotic component, and of course, water. The deep percolation is basically because the gravity pulls the water down. So we discussed about those. We also discussed about these four interesting principles that really borrow from the basic fluids about surface tension, contact angle, capillary pressure, and capillary rise, and we sort of applied these basic principles, assuming that the pore spaces in soil can be assumed as straight capillaries, and a bundle of such straight capillaries. So we kind of have established some kind of an analogy between the pore network, or the zigzag shape and size of the pores, to straight equivalent ideal capillary tubes. Then, of course, we talked about how water basically moves, water drives the water in terms of the driving force, and that we were able to link to the potential energy, and we introduced the concepts of soil water potentials, four different components we recognized, from gravitation to the pneumatic, and then of course we described how these total potential concept and the hydrostatic equilibrium are nicely bundled together into a very simple device to measure soil water potential. All right, so this is all about soil water potential, the energy status, the water retention characteristic, and the amount of water in soil. Hope you enjoyed it. Thank you.